So as we continue in the second portion of this section of our lecture, we'll start examining formulas, models, and equations that describe reactions. The atomic content of molecules can be represented in a few convenient formulas. We've already been using the molecular formula. The molecular formula gives atomic symbols and the number of elements that are involved in the subscript. For example, H2O or C6H12O6. So in H2O, there are 2 hydrogen atoms and 1 oxygen atom. However, these molecular formulas might not be unique. For example, when we look over here at fructose, galactose, and glucose, they all have the formula C6H12O6. However, they have a different arrangement in space. So it's very important then for us to consider the structural formulas, because these structural formulas illustrate the relationship of the atoms and the numbers and types of bonds. So the example on the right over here shows us fructose, glucose, and galactose in their structural formulas. These molecules with the same molecular formulas but different structural formulas are called isomers. Here are some other examples of structural formulas. Now on the printed page, molecules seem to appear pretty static, but this is not the real picture. Molecules are capable of changing through chemical reactions. So for ease of tracing these chemical exchanges between atoms or molecules, and to provide some sense of dynamic character, chemists use shorthand equations containing symbols, numbers, and arrows to simplify and summarize the major characteristics of a reaction. When we consider any reaction, there are both reactants and products. The reactants are usually shown on the left side of the page, and the products are the ones that are left over after the reaction has occurred, usually shown on the right side of the equation. However, the majority of these chemical equations or chemical reactions are bidirectional, so that is, they could go either forward or backward. On occasion, they are irreversible, just because the energy to drive it in reverse simply can't be provided. Now, when we break down reactions, we come into 3 different types. There are synthesis reactions. Those are the ones that build things, or anabolic reactions. It's where we have 2 reactants that bond together to form an entirely new molecule. We can see a few examples of that here. When we consider A plus B creates the molecule AB. We could also take some actual atoms and put them together. So sulfur plus O2 will give us SO2. Or 2 H2s plus 2 O2s will give us 2 molecules of water. Note that these equations must be balanced. That is, the number of atoms going in need to equal the number of atoms going out. The second type of reaction type that we might consider are decomposition reactions or catabolic reactions. This is where the bonds of a single reactant molecule are permanently broken to release 2 or more product molecules. So you can see here, the first example is exactly the opposite of the synthesis we saw. As I said, both of these reaction types can go forwards and backwards if it's energetically suitable. So we could take 2 H2O2 and split it into 2 H2Os and an O2. Again, these equations are balanced. Other terminology we might consider are dehydration reactions and hydrolysis reactions. Dehydration reactions are where we put 2 molecules together and pull out a water. That is, we dehydrate it by taking a hydrogen off one side and a hydroxide off the other side. We've created water and then bonded these 2 molecules together to create a new and different molecule. Hydrolysis is exactly the opposite of that. We'll see that we have a full molecule if we insert a molecule of water, putting a hydrogen here and an OH here, then we've created 2 separate molecules through hydrolysis or hydrolysis, using water to split the molecule. The third type of reaction that we'll consider are exchange reactions. In these reactions, reactants trade places between each other and release products that are a combination of the two. For example, here we'll say A and B plus X and Y. Once we interact with an enzyme, it could spit out two completely different molecules. So in this case, AX and BY have been created from the reactants AB and XY. Now, most reactions don't happen all on their own. It takes a catalyst to increase the rate of the reaction. For example, these reactions could happen, but it might take several thousand years for them to happen. But if we have a catalyst in place, then that catalyst, usually a protein or enzyme protein, in this case, we've brought in one molecule and broken it apart into two molecules using an enzyme catalyst. Now, enzymes are not the only catalysts, but certainly they're the most prevalent ones that we'll see in the biological systems. Now let's consider solutions. Solutions are homogeneous mixtures. That is, they're a mixture of one or more solutes that are uniformly dispersed in a solvent. When a solute is universally dispersed in a solvent, it cannot be separated from that solvent, either by filtration or by settling. A solute can be gaseous, liquid, or solid, and the solvent is usually liquid. Examples of solutions are things like salt or sugar dissolved in water, or iodine dissolved in alcohol. In general, a solvent will dissolve a solute only if it has similar electrical characteristics. A nice way to think of this is like dissolves like. You know that you can dissolve sugar or sodium chloride in water. And you know that vinegar and oil don't go together. This is because vinegar is polar and oil is nonpolar. So in the case of sodium chloride, as we can see below, sodium is positively charged, and thus it attracts the negative end of the water molecules that are surrounded. And so sodium becomes surrounded in a sphere of water molecules, or it becomes fully hydrated. In contrast, we can look at chloride. Chloride is negatively charged, and thus it attracts the positive ends of water molecules towards it. And chloride also becomes surrounded by a hydration sphere. So here we see like dissolves like. Polar molecules can surround charged or polar molecules. In biological systems, water is the most common solvent. And so let's take a little closer look at some of the interactions of water. We can divide solutes and solvents into three different classes. There are hydrophilic molecules. Those are molecules that attract water to their surface, just like the sodium and chloride that we can see below. These are considered polar molecules. Now, nonpolar molecules are hydrophobic. That is, they repel water. So oil is a great example of a hydrophobic molecule. It repels both water and vinegar. So can you guess whether vinegar is polar or nonpolar? Now, some molecules have both hydrophilic and hydrophobic properties. You may recall an old character from general biology called a phospholipid. We diagrammed a phospholipid similar to this. We have a phosphate head, which is hydrophilic, and then fatty acid tails, which are hydrophobic. They assemble themselves in rows where the tails are headed inwards in order to isolate them from the aqueous environment around. So when we consider solutions, we need to think about the concentrations. The concentration is the amount of solute that's dissolved in a certain amount of solvent. We can measure it by weight, volume, or percentage. Most commonly in biological solutions, we express them in molar concentration or molarity, where we say that 1 mole dissolved in 1 liter of water is a 1 molar solution. Now, you might be asking, oh, what is a mole? Whew, can't really recall that. Well, a mole is the molecular weight of the compound in grams. And how do we get the molecular weight? Simply, we add up the atomic mass of each of the atoms in a particular molecule. And there we have the molecular weight. So let's say you come up with a molecular weight of 36. then in order to make a 1 molar solution, you'll take 36 grams of that molecule and dissolve it in 1 liter of water. Another common way for us to consider concentration is by percentage. So if we were to make a 3% saline solution, we would take 3 grams of sodium chloride and dissolve it in 100 mLs of water. If we wanted to make a 30% solution, we would take 30 grams and put it in 100 milliliters of water. So you can see, either way we do it, making a specific concentration of a solution is relatively simple. Finally, when we consider solutions, we need to consider their acidity or alkalinity. That is the pH scale. Acidic solutions are when we have a component dissolved in water, an acid, which releases hydrogen ions. So by definition, an acid releases hydrogen ions into solution. We increase the concentration of hydrogen ions and it becomes more acidic. Basic solutions, the component will release excess hydroxide ions or excess OH. So a base, by definition, releases OH into the solution. The pH scale measures the acid and base concentrations of the solutions and ranges from 0, which is the very most acidic, to 14, which is the most basic. Remember that 7 is neutral. Now, pH is noted as the negative log of hydrogen ion concentration. These brackets here mean hydrogen ion concentration. So in truth, when we consider the pH scale, we'll see that a pH of 1 equals 10 to the negative 0 moles of hydrogen ions per solution, or that is 1. In the case of pH of 3, that means 10 to the negative 3 moles of hydrogen ions per liter of solution, or 0.001. As we move up through the scale, we get less and less hydrogen ions per solution. So a pH of 1 means that there are more hydrogen ions per solution and thus is acidic, versus a pH of 9 means there are many less hydrogen ions per solution and thus we're very basic. Let's have a quick concept check. What type of bond is formed when an electron is completely transferred from one atom to another? Let's consider that. What is an ionic bond versus a hydrogen bond versus a covalent bond? And we didn't even talk about van der Waals forces, so we'll leave those off the list. So transferring electrons from one molecule to another. Does that happen in covalent bonds? No, remember, covalent bonds were about sharing. So then we can take covalent bonds off the list. How about hydrogen bonds? Hydrogen bonds, we see them in water. No, not in water, but between H2O molecules, where the O is slightly negative and the H's are slightly positive. And then that slight negative and positive draw each other together. So we have a separation of charge and they're drawn to each other. But it's a pretty weak bond. It doesn't involve the transfer of electrons, so we can take that off the list. How about ionic? Ionic bonds. Ionic bonds were what we see with sodium chloride. And why does sodium stick to chloride? Because sodium's positive and chloride's negative. And so in order to get positive or negative, they must have gained or lost a complete electron. So that's electron being completely transferred is the key here, and ionic bonds is the correct answer. So far, we've only considered the smallest and the simplest components that play diverse roles in the structure and function of living things. These are things we consider inorganic chemicals. They usually don't contain either carbon or hydrogen. For example, we've looked at sodium chloride, so there's no carbon or hydrogen in there. In contrast to inorganic chemicals, we have organic chemicals. Organic chemicals are carbon-based compounds that have a basic framework of the element carbon bonded to other atoms. Most of the chemical reactions and structures of living things involve organic chemicals. Below here, you can see an organic chemical. It consists of these black carbon molecules with hydrogen molecules in white attached to them, as well as the addition of a functional group. The majority of organic chemicals involve some form of hydrocarbon skeleton, even if it's only one carbon long, like in the sense of amino acids. And they also involve a functional group that makes it specialized. So why is carbon so important? It all comes down to the valence electron arrangement in the outer shell. It allows for 4 bonds to be made. Because of these 4 bond possibilities, it can form a linear, branched, or a ringed structure. We can form single bonds in the linear structure, as you can see here, in this linear carbon molecule. Or we can see branched bonds, or we can see double bonds. And sometimes even these linear carbon strings will form a ring, as we've seen with the structure of glucose. Most often, these carbon chains are associated with the sponge elements, minus the C, of course, because that's the base of it. So sponge without C are what form these specialized functional groups that give organic compounds or chemicals their unique features. Let's look at some of those functional groups. Functional groups are special molecular groups that are composed of organic compounds. These are the portions of the hydrocarbon chain that give the compound their unique reactive properties. You can see just a few of the functional groups that are most common in biology. For example, an alcohol functional group is this OH. An aldehyde is a COH. Ketones, another common one we'll see here with a double bond to O. Anyway, if you were to take organic chemistry, you would learn many of these functional groups that give our organic compounds their unique reactive properties. So in summary, organic compounds are formed by a hydrocarbon chain plus some special functional groups. Now that hydrocarbon chain may be a varied number of lengths. It could be single bonds between the carbons or double bonds between the carbons. And thus we can form branched or unbranched or ringed structures, in addition to adding these functional groups to give them some very special characteristics. This brings us to the end of this section of our chemistry chapter. But before we go, let's have a quick concept check. What kind of reaction do we have illustrated here? We have 2 H2s plus an O2. We can rearrange these and come up with 2 water molecules. So of the different types of reactions that we considered, what do we have here? Let's consider one that's not even on our list. We'll get rid of that right away. Spontaneous. Was it decomposition, synthesis, or exchange? Take a moment to think what each of those were. Were we swapping things around? Or were we making something new by adding 2 components together? Or are we breaking something down? Well, we're certainly not exchanging anything. And I think that it's probably synthesis. Decomposition? No, I'm going to go with synthesis because we've brought the 2 H2s together with the O2 to create a totally new molecule. Thus, B, or synthesis, is the correct answer. This would be a great time to spend some energy in diagramming. Take a moment to think about ionic, covalent, and hydrogen bonds. Diagram and distinguish between each of those bond types, and make sure you consider which is strongest and which is weakest. Then you'll be ready to move on to the next section of this chapter.